1 gram, $62.5 trillion. That is the price of 1 gram of antimatter, the most expensive substance ever created in the history of human civilization. It takes the most powerful machines ever built just to make a few atoms of it. And if it ever touched your hand, the explosion would be instantaneous. No residue, no crater, just pure energy, released all at once. Antimatter is real. It is being made right now, and its existence points to one of the deepest unsolved mysteries in all of physics. So what exactly is it, and why does the universe have any at all? To understand antimatter, you first have to understand what ordinary matter is made of. Every atom in your body, every atom in everything you have ever touched, is built from particles called protons, neutrons, and electrons. These particles carry specific properties: mass, charge, spin. Now imagine a mirror universe, identical in every way, except every single charge is flipped. The electron, which carries a negative charge, has an antimatter twin called the positron, identical in every way but positive. The proton has an antiproton, same mass, but negative charge. Combine an antiproton with a positron and you get an antihydrogen atom, the simplest atom of antimatter ever created. This is not science fiction. Scientists at CERN, the European Organization for Nuclear Research, buried under the border of Switzerland and France, have been creating and trapping antihydrogen atoms since 2010. The antihydrogen doesn't last long, measured in fractions of a second before it touches the walls of its container and annihilates. But keeping it alive even that long is one of the greatest technical achievements in scientific history, because antimatter cannot touch anything, not air, not metal, not glass. The moment it does, matter and antimatter collide, and both are instantly converted to pure energy. That conversion is called annihilation, and it is the most efficient energy release in all of known physics. Nothing we have ever invented, not nuclear bombs, not fusion reactors, comes close. A single gram of antimatter annihilating with a gram of matter releases the energy of a nuclear bomb 40 times more powerful than the one dropped on Hiroshima. From 1 gram, the weight of a paperclip. So why does it cost $62.5 trillion per gram? Because making antimatter is almost incomprehensibly difficult. To create antiparticles, physicists accelerate protons to 99.9999991% of the speed of light inside a 27-kilometer circular tunnel. Then they smash those protons together with enough force to briefly recreate the conditions that existed just after the Big Bang. In that fraction of a second of chaos, antiparticles flicker into existence. They have to be caught immediately, using powerful magnetic fields before they touch anything and vanish. CERN's entire accelerator complex, costing billions of euros, employing thousands of scientists, produces roughly 10 nanograms of antihydrogen per year. 10 nanograms, that is 10 billionths of a gram. At that production rate, it would take more than 100 million years to produce a single gram of antimatter. The electricity alone, required to run CERN's accelerators, costs hundreds of millions of dollars every year. That is why $62.5 trillion per gram is actually a conservative estimate. The danger, however, is just as staggering as the cost. If the magnetic field, confining even a nanogram of antimatter, were to fail, perhaps from a power cut, the annihilation would be immediate. The resulting gamma radiation would be lethal to everyone in the building. This is why CERN's antimatter facilities are behind multiple layers of shielding and are never left unmonitored. But despite its terrifying power, antimatter has also inspired some of the most ambitious dreams in science. NASA and the European Space Agency have studied antimatter rocket engines, spacecraft that would use the annihilation reaction as thrust. The math is extraordinary. A single gram of antimatter could propel a crewed spacecraft to Mars in roughly 6 weeks. With enough of it, we could reach the nearest star system, Alpha Centauri, in as little as 40 years. Antimatter is the most energetically perfect rocket fuel the laws of physics allow. There is also a medical side to antimatter that is already saving lives. PET scans, positron emission tomography, work by injecting patients with a tiny quantity of positrons, the antimatter twin of the electron. Those positrons annihilate with electrons inside the body and release gamma rays that cameras outside the skin can detect. The result is a three-dimensional map of metabolic activity inside a living human body, one of the most powerful diagnostic tools in medicine. Antimatter built for destruction is also, quietly, helping doctors find cancer. But the deepest mystery surrounding antimatter isn't its cost, or its danger, or even its potential. It is the question of why we exist at all. When the universe was born, in the first fractions of a second after the Big Bang, it created equal amounts of matter and antimatter. Equal amounts, which means they should have annihilated each other completely. The universe should have ended up as nothing but a sea of gamma radiation. No atoms, no stars, no planets, no life. And yet, here we are. Somehow, for every billion pairs of matter and antimatter particles that formed in the Big Bang, one extra matter particle survived. Just one. And those surviving particles became everything. Every galaxy, every star, every atom in your body. Scientists call this asymmetry between matter and antimatter, CP violation, charge parity violation, meaning the laws of physics are not perfectly symmetrical. Something, somewhere in the fundamental rules of the universe, slightly favors matter over antimatter. We can measure that asymmetry, but we still cannot explain it. This is why the experiments at CERN's alpha and base experiments, trapping antihydrogen and antimatter atoms, matter so profoundly. Physicists are examining antihydrogen with lasers to see whether light behaves identically when it interacts with antimatter as it does with matter. So far, to our best measurements, antihydrogen looks exactly the same as hydrogen, which deepens the mystery rather than solving it. In 2023, the Alpha collaboration made history by measuring the effect of gravity on antihydrogen for the first time. They confirmed that antihydrogen falls downward, just like ordinary matter, not upward, as some theorists had speculated. That was a crucial data point, but it still leaves the central question untouched. Why did matter win? The answer would not merely win a Nobel Prize, it would explain why the universe contains anything at all. And that means every experiment done at CERN, every atom of antihydrogen trapped for 1,000th of a second, is a question aimed at the deepest level of reality. Somewhere beneath the Swiss countryside, in a tunnel colder than outer space, physicists are trapping fragments of a substance that sells for $62.5 trillion a gram. They are doing it not to get rich, and not to build weapons. They are doing it because a single gram of antimatter contains a question that has haunted physics for a century. The universe should not be here. Every galaxy, every ocean, every human life exists because of an imbalance so tiny it is almost nothing. One extra particle for every billion. We are the descendants of a cosmic accident so improbable it has no satisfying explanation. And the most expensive substance ever made is our best tool for finding one. The universe left us a clue in its own mirror image, and we are only just learning how to read it.